Orbita is the official journal of UMALCA, the Union of Mathematics in Latin America and Caribbean. And in this, it's my great pleasure to introduce this edition's speaker, Julia Plavnik. Julia is an Argentinian mathematician and the Charlotte N. Griffin Associate Professor of Mathematics at Indiana University, Bloomington. She earned her PhD from Universidad Nacional de Córdoba in 2013 and has held postdoctoral positions in Argentina and in Texas. She received the Humboldt Research Fellowship in 2023-24. She's also supported by an NSF career grant and serves as PI for the Simons Collaboration on Global Categorical Symmetries. Julia is also a great mentor for students and postdocs, having received the 2022 Outstanding Faculty Mentor Advocates Award from Center of Excellence for Women in Technology at Indiana University. Julia's research is on quantum symmetries, with a particular focus on quantum algebras and quantum topology, as well in the connection of tensor categories with other areas of mathematics and physics. So today, Julia is going to tell us about contragredient Lie algebras in symmetric tensor categories. Please, Julia.
Yeah, thank you, Carolina, for the introduction. Let me share again the screen. And thank you to all the organizers of this great webinar for having me here. I'm very honored to be part of this series of talks. And yeah, and I have joint work with Iván Angiono and Guillermo Sanmarco in this journal, and I'm very happy. I love that Micah started this journal, and I'm really honored to be giving this talk. So I will tell you a little bit about this joint work with Iván and Guillermo, two friends that I met during grad school in Córdoba, and we are now collaborating in a couple of projects. And so part of the story I will tell you about, it's the paper that we have jointly in Orbita journal and some other follow-up work. So maybe before going to the meat of the story, let me tell you a little bit about the motivation. So there are a lot of words, and maybe sounds very technical: contragredient, a special class of these Lie algebras, and then symmetric tensor category. So I wanted to say before getting started and giving the definitions, maybe some perspective on why studying tensor categories or symmetric tensor categories. So at least for me, I started in Córdoba, and I come from algebra background. I was studying some non-commutative algebras as itself, trying to understand them, classifying. And then I discovered that when you look, or not I, but I was introduced to this word, that when you study the collection of representations of these special algebras, the collection, when you start looking at them all together, they form, or they have a nice structure, they are a category, and that can give you some perspective. In particular, they form these tensor categories, which are a natural host, or they are thought as natural host for symmetries in more general contexts. For example, in quantum contexts, when you want to study things that are very small, and groups are not longer enough to describe the symmetries of these objects. So in particular, with this idea of symmetric tensor categories, the perspective is more or less that, like, people was very interested in studying representations of groups, algebraic groups, and different objects. And at some point, more like maybe as a modern point of view, they started studying all the representation together and all the maps affect the action or the intertwiner together. And they started studying these categories that happen to be these symmetric tensor categories. And then we want to, these kind of categories have some linear algebraic flavor, so we want to start doing things that you do when you have vector spaces, but now in this maybe different setting, and try to see if we can get new exotic things there, or maybe if we can prove things that are hard to prove in the regular setting by looking in this kind of different way, with this different perspective. So just to start, let's talk about what is a category. So in a category, we have objects, collection of objects, and then I will have maps between my objects, the morphisms. So each time I have two objects, I will have this home space, which will be all the arrows between these two objects in my category. They need to these maps need to have some conditions. In particular, I want to have this operation of composition when possible, like the usual composition that you can imagine. And I want this composition to be associative. And moreover, each time I have an object, I want to have an identity map between the object and itself. That I didn't write what means to be the identity, but that behaves well with composition in the usual way. So some usual examples that maybe you find in nature of categories are things that, I don't know, that are like you are studying some kind of mathematical object, and the category could be the collection of these mathematical objects, for example, sets or topological spaces or vector spaces. But then to understand these objects, what we usually do is we try to understand the arrows between these objects. It's one way to understand the objects better. So for example, in sets, we study functions. In topological spaces, we study continuous functions. In vector spaces, we study linear functions or linear transformations. And that are these categories on this side. But there can be different kind of categories, some more abstract ones. And one that I really liked it when I learned categories was this one. You can start with a group G and think of this and create a category out of it. How we do it, we have only one object in this category. So now I need to tell you how we can describe or what are the maps in this category. And the maps will be the elements in my group G. And now I need to give you the composition, like the composition operation. And I have an operation in my group, and I will use that. So the composition will be the product in the group. And the identity map that I need, in this case, I only have maps between X and between the star, this only object and itself. And so the identity will be the identity element for the product. To be totally honest, here I didn't use all the group structure. I didn't use the inverse. So as you can see, you could do this with a little bit less structure, but just in case, I use group because I learned it that way. So now, in the same philosophy, now I'm studying categories. I want to understand maps between categories. And that's the notion of functors. And I mention it here because we will be using a little bit functors in this talk. So if I have two categories, I want to describe what are maps between these categories. So they are maps that behave well with this structure that we have. So a functor will be a map that sends objects to objects. So if I have an object in C, when I apply my functor, I will get an object in my category D. And it does the same with functions. So if I have a function from X to Y in my original category, when I apply the functor, I get a new function between f of X and f of Y. There are other functors that change the order of functions, but I will stick with these ones, maybe, because, yeah, okay. There are other functors that change the order of this, but I wanted to say this one. And I want my functor to behave nicely with composition and with identities. And some usual examples are forgetful or inclusion. For example, in the other page, I was telling you, okay, we have vector spaces, or we have topological spaces. So underlying, usually we have some structure, and I can use that. For example, let's say that I have a category of modules. I'm looking at the modules over a group, for example. And I could forget that these modules are modules that have an action of my group, and just think of them as vector spaces. And that will give me a functor from the category of that modules over, I don't know, G to vector spaces. And that are the ones that are forgetful, for example. But I could also look at the category of, I don't know, abelian groups, and also the category of groups, and I will have an inclusion in that case. Of abelian groups in the category of groups. In that case, the maps will be group homomorphisms, and in the case of abelian groups, they are still group homomorphisms because I didn't. The idea of being abelian is just a property of the group. It's something that happens or not, so I don't need to require any extra thing in my maps, in my morphisms. They will be just group homomorphisms. And here I wanted to put an extra example. So if you have vector spaces, you can have the dual vector space. So you could take duals, and you can also take the transpose maps, and that will give you some example of a different kind of functor. I was just wanted to give another flavor of functors. So now I want to go and I want to define what a symmetric tensor category is. If you have here at some point about tensor categories, it might be scary because it has a lot of, like, the definition is long. So what I wanted to do is I want to give you an example first and look at that example and see what we like about that example, and then from there go to the abstract definition. So for this, what I will do, and in the whole talk, for me always, K will be an algebraically closed field. So I will not say this anymore, but K for me will be always a field and algebraically closed. Otherwise, some things go kind of wrong when you forget this or this. But the characteristic of the field will be changing depending on the case. So what category I will be looking at? I will be looking at finite dimensional representations of my group G. I usually will be focusing on representations, but another way to see this, and it's the same, is if we think of modules. And here I wrote it more in the modules way because I thought that was a little bit easier to digest. So if we think that we have some vector space with a G action. So what I like about this category, there are many things, but for example, if you give me two modules over G, then I can cook up a new one by taking the tensor product. So what is this module? As a vector space is just the tensor product of vector spaces, but then I can act with this so-called diagonal action. I can act in each component of the tensor product with the same group element. Then one other thing that it's nice is that my field, which is a K vector space, is actually a G module itself. How? With this trivial action. I act in any element trivially. I don't do anything to any element in the field. Other thing that it has that it's nice is that, again, if you give me one representation, I can give you back another one. Which one? The dual. The dual vector space, but I will equip it with an action that is sometimes called contragredient action. And how we act. So if I have T, this T will be in V dual. I want to act and I want to get a new thing in the dual. This is just the linear dual. Linear functions from V to K. So I need to tell you how this new function is in each element of my vector space. And okay, now I want to really use the action that I already had. So in principle, we could have act with G, but that will not give you really a module. So you need to act by the inverse of the group element. So here you see I do need a group here, not like in the other example. Other thing that it's nice in this case is that there are Jordan Holder series. So we have some sequence. So if you start with one of these like V that it's a representation or G module, then there exists simple G modules, and I will be able to put them in a chain until I get to the last one that is mine. And so the V modules that I will be getting simples, let me write it here because I didn't do a good job saying it. These things here will be simples or irreducible representations, maybe I should have said. So this is the nice property that this sequence will be having. They will be irreducible representations or irreducible modules. And the last thing that I wanted to mention here that it's interesting, I mean, this category has a lot of good things, but this tensor product that I told you here, it's actually commutative in a kind of a very, very coherent way. And later I will tell you what I mean with coherent. But what I mean is that because you see, you're acting in the same way in both components. Actually, if I do W tensor V, it's also a G module, and I have this nice isomorphism between them. Oh, maybe there I don't want the arrow. And this is just the swap. The map is just given by the swap of the tensors. But what is important about this? I mean, you could tell me, oh, you can always do the swap. That's fine. But what is important is that this map is a map in this category. And I only told you here what were the objects. The maps were intertwiners or maps of G modules, so things that behave well with the action. And exactly because the action is diagonal, this is fine. It's a map in my category. So now let me tell you what it's a symmetric tensor category. Again, it's a long definition, but we can go back always and think about the Rep G case. Or if you don't like groups that much, you can think about finite dimensional vector spaces, and we'll do it for you in the same way. So just to say that I will be all the time using STC for symmetric tensor category. So a symmetric tensor category over my field, here it's important that I have my field K, is a category that has some structures and some properties. So I will tell you first which structures. The first structure that I want is that it's abelian K linear. What is this? So abelian means that basically I can do things that I can do in the category of modules, so that I have direct sums, kernels, and co-kernels of maps. But if this sounds too abstract, one way to think, there is a nice theorem by Freid-Mitchell, any abelian category can be seen as a full subcategory of the category of modules over some ring. So full just means, like, I have a subcategory. What is a subcategory? Category inside other. But full means that the morphisms between the objects in my subcategory are the same morphisms than in the original one. So I inherit the morphisms. I only restricted the objects in this case. So what I mean is, if this sounds a little bit obscure, maybe just think that it's a subcategory of a category of modules, and that you are inherit the nice things that the category of modules have. And basically what we want to do is we want to be able to write exact sequences in this kind of categories. K-linear, on the other hand, means that my home space in my category will be a K vector space. So this category that I have here is enriched over the category of vector spaces, meaning that I have some nice linearity here. And that's where the field K is important, and that would start changing all the things in the different settings when you drop algebraically close, which gets very wild, or when you change the characteristic of the field, as you will see in a little bit. So these are the first structures that I will be asking. And then I will be asking for more structure. I want a monoidal structure. That is basically what I was kind of hinting here. So I want to have a tensor product in my category that will be a bifactor that takes two things in C and give me another thing in C. I want this tensor product to behave well with the abelian structure. So I want to have some things that work well together in objects, but also in the morphisms, in the morphisms. And I want this to be associative. I will tell you in a minute what I mean. I want this tensor product to be unital and also in coherent ways. So I will write it like this, and I will explain now what this is in words. So associativity. Usually when you have these monoidal categories are like a categorification of the notion of a monoid. So basically, I could use this tensor product repeatedly. And for example, if you give me now 3 objects, I could do the tensor product of 2 and then the third one. Or I could do the tensor product of the last 2 and in the left, the first one. And I would like this to be the same. I would like associativity. But in category theory, it's too much to ask for equality. So what we do is we ask for just isomorphisms, natural isomorphisms. So changing parentheses will be fine, but it will be an isomorphism. Then I want to have a distinguished object in my category that it's the unit for my tensor product. And again, to say that it's the unit, it's saying that X tensor 1 is isomorphic to X, and that will be via a left isomorphism, natural isomorphism, and 1 tensor X is also isomorphic to X via a right isomorphism. And then I have here these weird symbols, meaning that I wanted to tell you when you're working with category theory, you have a lot of commutative diagrams. In particular, this is called the pentagon axiom and the triangle axiom. This pentagon axiom, to say it in words, what it says is, okay, for the tensor product of 3 objects, I'm fine. I have this associativity constraint. But what if I do 4 now? Okay, if you do 4, there are 5 ways to put parentheses on these 4 elements. That will be the vertices of my pentagon. And then these lines in the pentagon will be maps in the category, and basically will be associativities or associativities tensored identity. And I will be basically saying that going in one direction or the other is the same. So I'm saying that basically the different ways to put the parentheses are fine, and yeah, some coherence. And for more parentheses, for more objects, basically, not more parentheses, but yeah, putting parentheses in more than 4, now is instead of an axiom, it's a theorem, MacLane coherent theorem, that you can put more and do it in a coherent way, and it will be fine. That follows from this. And the triangle is just the relation between L, R, and alpha. Now, here we have the tensor product that I mentioned. We have the field in the previous slide that I mentioned that was a representation, and I told you, okay, I also like that I can have duals. This is rigidity here. Is the existence of duals left, maybe let me say, left and right duals for all objects in the category. And I don't want to say precisely what it's left and right duals, because it will get longer, but it's not just an object. It's an object together with 2 maps called evaluation and co-evaluation that give you some zigzag axioms, some things that you can, when you compose them in some way, you can get the identity back. But what is important is that, for example, in the previous example, I asked for the example to have finite dimensional representations. And that was not because I like it only. It's because if you want chance of rigidity when you have vector spaces, underlying, you need finite dimensionality. So it's not just having the V dual, for example, for vector spaces. You want this dual object, which in that case is the linear dual, and the evaluation to be able to be a triple with an extra map that is called co-evaluation that satisfies certain axioms. And for that axioms to be axioms being satisfied, force the vector space to be finite dimensional. So this is giving me some finiteness around. The next condition that I'm doing is kind of mixing condition between here and here. So let me say this here is a property of being monoidal. If I have a monoidal category, it's rigid or not. It has left and right duals or not. But this one here is a mixed condition. Why? Because the 1 is something in my monoidal structure, and K is something that I was like looking here. It was something that I asked when I asked K linear, that this is a vector space and I want this vector space to be K. And then maybe I should have done a pink thing here. The other thing I wanted to say is in this symmetric world, I want to have this commutativity of my tensor product. Again, I want this to be coherent. So being commutative means that I have a family of natural isomorphisms between the tensor product in one order and the opposite, x tensor y and y tensor x. And it's not just that. I want, as I want it here, I want 2 axioms called hexagon axioms. These hexagon axioms basically are encoding the braid relation, or other way to say it, they are telling me how this map that I call the braid between X and a tensor product can be written in terms of associativity and the braid of X with each of the components of the tensor product. And I have 2 axioms because I could ask the tensor product to be in the second or in the first component. But something important here is that we are not talking about any braided categories. We are restricting to these ones that are called symmetric. This is very special. And it's when you do the braid twice, you get the identity. So the inverse is the braid itself, basically. And this is related to representations of symmetric groups or things like that. If you drop this hypothesis, you get representations of the braid group more in general. I will be usually working, even if I just say symmetric tensor category, I will be working always in this more special word in which the objects, I told you that they have this Jordan cell holder series, that series always is of finite length. So maybe I wanted to write a little bit, I wanted to tell you a little bit about Lie algebras. I know that this might be known for some people, for some other not. So I wanted just to tell you a little bit of what is a Lie algebra, because it's part of what is in the title of the talk. And I thought, okay, let me tell you a little bit, and will be kind of a key example. So what is a Lie algebra? I will start with a vector space over K, sorry. And I will have this map. So what I want to have is an algebra, but this algebra is not associative in this case. So the product of my algebra will be denoting it with this bracket, and this will be satisfying two things. One is that it's symmetric. So just that I will have this. And here, the characteristic, I mean, this is for, sorry, and I wrote it wrong because I wrote it symmetric. Sorry. And this is for a characteristic different of 2, because otherwise I would be asking the bracket of xx to be C. I will be having that. So this is for characteristic different from 2. And then the other thing that I want, it's the Jacobi identity, because I told you that this is not associative, so I want to see the relation between things. And so I will write it in this way that I like it, just kind of permuting the things, and I will add them together, and what we will get is that give us 0, but basically you can recover one from the other. And what is nice, and maybe I will not go in details here because I know that I'm going a little slower than what I wanted, is that, okay, maybe let me say one more definition and then I will say the result, and maybe I will not go in all the details. But what we can do when we have Lie algebras is also talk about modules, like what we were doing with groups. And what will be a module? It will be just, again, a vector space. And I will have an action of my Lie algebra on my vector space. And I want this to behave well, as usual, with the structure that I have, in this case, the bracket. So I will ask that if I have, if I have acting on some V, I can see this as some actions coming from the independent elements. What I want to say about this is that, and I was going to give all the structure, but I'm going a little slower than anticipated, is that I can look at the category of modules as we were doing. And here I want finite dimensional. I will not say it, but always I want finite dimensional, even if I don't write this here. And this is, again, a symmetric tensor category. And here also, yeah, if you do the finite dimensional. And the thing is that what it will happen is the same as happened in the other case. I will have a tensor product. In this case, the tensor product will not be the diagonal. Here, I will have something more contragradient, acting a little bit different. The field will be, again, the unit of my monoidal product, but now the action, it will be trivial in a different way. In the other, I didn't do anything. In this one, I will send it to 0. The dual will be, again, a module, because I'm finite dimensional and because I can, but instead of acting with the inverse of an element, because here I don't have the inverse, I will act with the opposite of an element. And again, the usual flip will do the trick to have a symmetric braiding. So before going to the more definitions, I wanted to give one more example, because I thought that this example could be also helpful and familiar, and basically because I will be using a lot this example. So this example is supervec. What is supervec for me? So as you imagine, it's related to vector spaces, but now instead of being just vector spaces, this will be finite dimensional, set to graded. That's why we have super, K vector spaces. So how are my objects? My objects decompose as a direct sum of some subspaces here of V. And how are the maps? The maps here, I want to respect the grading. So if I have the home in S-vec of V and W, remember when I write here V and W, I'm abusing of notation because actually I need to tell you who is the grading. So maybe I should write something like this for you to be more precise. These are just linear transformations because these are vector spaces. So I want that to be respective, but also I want this to respect my grading. That are the home spaces. And again, I will be able to have a tensor product, and this is by parity. So if I have the tensor product as a vector space is the product of the vector spaces, the tensor product, but now I need to tell you the grading. And what I will do is I will respect somehow the parity. So everything that will give me parity 0, if you here 0 plus 0 will give me 0, and here 1 plus 1 will give me 0, and now the mixed ones will be the ones. Sorry. These will be my vector spaces. The unit in this case will be just k, but concentrated in degree 0, let me say, so degree 0 here. And the dual will also be there. I will not write this, but what I do want to write is something important, that it's the braiding. So maybe let me write how is the braiding. So instead of being just the flip, I will have the flip, but I will switch the flip a little bit by a sign, and the sign will be determined by the component in which this V and W are homogeneous element in which this lives. So it's kind of a parity. Okay. So these are some examples. Now, again, I told you, if I'm studying categories, what I want to do is I want to understand also the functors between things. So let me tell you a little bit about this. Now, if I have these symmetric tensor categories, what will be a symmetric tensor functor? I mean, of course, I want a functor, and these tensor categories have monoidal structure and symmetric structure. Remember, this is something about the monoidal structure. So I want both of them to be respected. Means, I mean, I will not say it precisely, but I want to say that there is some map that sends f of the tensor product to the tensor product of the f's, and there will be diagrams, and the braid is respected. The braid has also some diagram that need to satisfy. In this case, the symmetric braid. But I also want to play well with my other structures that were the abelian and k-linear. So I want the functor to be k-linear, so it needs to behave well with the vector space structure. And exact is related to this thing that I told you, that I wanted to be able to do basically homological algebra. I wanted to have exact sequences. So exact functors will be functors that send exact sequences here to exact sequences here. I know that it's a little bit technical, but what you need to think is that these are the correct functors for our setting because we want them to preserve all the structure that we have it. So as I was saying, some class of usual functors are the forgetful functors. And in this case, maybe let me pick a color. These are both symmetric tensor functors. The ones that are in here, finite dimensional representations of the group G or finite dimensional representation of the Lie algebra G to vec, they both are well behaved. And the same for the inclusion from vec to S-vec. We're picking things that are concentrated in degree 0, and that's how vec could be seen inside super vec, and that's well behaved. But there is no any, so if you have a monoidal or tensor factor, or if you want to look for a symmetric tensor factor, you will never find it because the braid will, since here I have a sign, and here I don't, when I try to write a symmetric monoidal functor, I will fail. There are none of them. So in this case, we don't have. So let me tell you maybe motivation to study, or what kind of questions to study in symmetric tensor categories these days. So in characteristic 0, and I told you we will be playing with different characteristics. In characteristic 0, there is a very beautiful theorem by the Lignès. And what he was able to do is he was able to fully classify symmetric tensor categories of a specific class that I will tell you in a minute, of moderate growth. But basically what I'm saying is that they have some finiteness or some control on the size. And they always look like rep G. But here G, it's a little bit maybe more complicated. So it sounds easy, but these G are affine algebraic supergroups. But in any case, what I wanted to bring here is that, okay, for algebraically closed characteristic 0, well-behaved in size, we know how they look. They look like rep G for this. Let me give you 2 comments. One is the definition of moderate growth, because I didn't tell you. We have this notion of length. What we are asking is that this moderate growth is taking, I mean, we have finite length, but we want them to grow at a good pace. So for any object, there need to be some real numbers, positive real numbers, that the length of the power of my object is smaller or equal than the power of this real number attached to my object. So the powers growth at an exponent, moderate growth given by this, the thing that we're picking for this x. Let me tell you one case that maybe it's a little bit easier. When the symmetric, particular case maybe, there is a particular case in which this works very well. So if you are in symmetric tensor, maybe let me say a fusion, maybe a symmetric fusion category, and I will tell you what it is, fusion, in characteristic 0 again, here this is important, it's always rep G set. But now, why I wanted to mention this one is because it's a little bit more digestible depending, like the definition of fusion and the answer. But fusion means that it's semi-simple, the category, and that I have finitely many simples, only that. Semi-simple is that every element, every object in my category can be decomposed as a sum of simples, and simples are objects that have only a subobject, 0, and itself. So if you are thinking on groups, so the simples are the reducible representations, and semi-simple means that the category is completely reducible. And this will be playing a role. That's why I wanted to mention. And here, in this case, this group is a finite group, and this set is a central element. So for example, supervec is set 2 with the non-trivial central element. And all the categories, all symmetric fusion categories are this shape. Of course, this is the more general result, but just to have a particular case in mind. So what kind of questions, right? It is it's always true, because here we have some specific words that I was mentioning. One was restricting the word to symmetric, because I told you, okay, we're asking for this very cute condition that the square of the bracket give you the identity. The other was this nice condition on the size of the tensor powers of the elements. And the other was the characteristic. So each of these open a huge world. If you don't ask for symmetric, there is a lot of study, and I particularly work a lot on this, on braided and modular, and even without braiding, but fusion categories. Maybe tensor categories or fusion categories, tensor, let's say, because. So there is a lot of work. Here, there are a lot of examples that don't fit in this work, but are still interesting. The linear categories, for example, which at some point, the Linear and Milner were studying some categories, and they look at these interpolation categories, and then the linear prove some more general results. And there is a big world out there to study these very interesting categories that satisfy different or behavior than the ones that we will focus. But today, we will be focusing on this, on characteristic P. So why characteristic P is interesting? For example, our main example, the one that we use it as a toy example to give the definition. If the characteristic of the group G, of this finite group G that I started, is divisible by P, now the category is not completely, or the representations are not completely reducible anymore. So there is Maschke theorem that tells you how this is behaved, but my category, so the representations of a finite group are, or the category is semi-simple, or every representation decomposed as a finite direct sum of irreducible ones if and only if the characteristic of the field doesn't divide the order of the group. So now we are losing semi-simplicity. Semi-simplicity is very handy to do a lot of things. And now we will not only have the irreducible representations, we will also have indecomposable representations. So what do we do? Maybe we want to go back to the comfort of semi-simplicity, and how can we do that? That's what I will kind of tell you now. The idea would be, can we get a semi-simple symmetric tensor category from a non-semi-simple symmetric tensor category? And the answer is yes, there is a process of semi-simplification. Different people study this, but there is a paper by Ettinghoff and Ostrich on this. And the idea is that we will kill some morphisms, so we will have more isomorphisms in some way. So let me tell you the definition, but later I will tell you what we care. So if this sounds a little bit crazy, don't worry, we will look at a specific example. So if I start something on what I'm saying here, something that, or here, in my category C now, I will have indecomposable, if I mean non-semi-simple word, I will have indecomposables, and what will happen is in my new category, this will be my semi-simplification. The things that in my original category have dimension 0 will be 0 in the other category. So I will be killing somehow some of the indecomposables, and now they will be 0 and I will be fine. But let me tell you what's the idea. So how I create my new category. I will start with some symmetric tensor category, in principle non-semi-simple, and I want to define this semi-simplification. So I'm doing some kind of quotient of the category. The objects will remain the same. I'm not doing anything. What I'm killing are morphisms. I'm killing by these so-called negligible morphisms or negligible map that they form a nice tensor ideal. If you know what it is, great. If not, doesn't matter, but that's what makes things work well. And what means negligible, we have a notion of a trace, and a map is negligible if for any other map that's going in the other direction, when I compose them and I get now an endomorphism of X, the trace of that is 0. So are the things that somehow they get trace 0. So I'm killing that, and the result is that I get a new symmetric tensor category, and that one is semi-simple. If I started with a semi-simple, the result is the same because basically this is 0. I don't have anything. So maybe let me tell you a little bit about this. This gives rise to a functor from my original category to the semi-simplification. This functor is more or less well-behaved. It's monoidally symmetric, but not exact. It will not take exact sequences and exact sequences, but it's quite well-behaved. It's preserving part of what I wanted. And these are the results that I want you to keep in mind. If I started with an indecomposable, that the trace of the identity or the dimension, which that's the definition, it's 0, that will be 0 in my semi-simple category. So it will not be bothering me. And then who are the simples? Because in a semi-simple category, the simples determine all the other things. So who are the simples in my semi-simple category are the indecomposable in the original category that didn't have dimension 0. So my indecomposables are basically what I'm interested in the non-semi-simple category. The ones that are of dimension 0, they go to 0 in the semi-simplifications. The one of non-zero dimension are the simples in my semi-simple category. So let me give you an example, and that's why characteristic P is super exciting. In characteristic 0, we didn't have new examples. We have basically this representation of these affine algebraic groups, but in characteristic P, we have new examples. How we get it? By semi-simplification. We look at the smallest example. We look at a simple group of a cyclic group of order P in characteristic P. Now this is non-semi-simple, and I will semi-simplify and get a semi-simple category. Who are the simples? I told you, are the indecomposables in my original category that were not of dimension 0. Who are them? Are the images, in this case, of Jordan blocks of size I. So I will have P minus 1 of them. LP, in principle, because I could go to size P, that one will be 0 when I semi-simplify. And the first one, the size 1, will be the unit of my, of my new category, of my semi-simplification. These categories are called Verlinde categories because these here, that are the fusion rules, is the Verlinde, it's kind of a Verlinde formula. And maybe it doesn't matter that much what it says in itself, formula, but let me tell you that we know exactly the fusion rules that come from this Verlinde formula that it's important in quantum groups and things, and you can express it in some ways. I gave you some examples here on how this is working. I wrote this here because when you are in characteristics 3 and you don't, before semi-simplifying, you want to compute this is actually 2 copies of L3. But L3 in characteristics 3 will be 0, and it's fine, we get 0 also when we do the formula. So, because yeah, we get something different, but it's both in both sides 0, so we are fine. Something interesting is that the last one, the size p minus 1, when you tensor with itself, give you the unit and move a little bit the other ones. But okay, we have this nice formula that comes or that looks familiar from other contexts. So let me tell you a little bit more things that we like. The unit always generate the category vec, and also these categories inside the category generated by these ones that I told you, the p minus 1, that is square to 1. So, and that's actually super vec, the category that I was telling you. So we have a copy of super vec inside verb p for any p. And actually, if we now look at the odd labels and you go back to my Verlinde formula that we will not do now, but if you go back, when you tensor them, you get a tensor subcategory. If you tensor things that are odd, you get something odd again. And that it's this verb P plus subcategory. That is very nice because verb P decompose as a direct product of categories. It's called the linear product of tensor categories of these odd labels and the supervector spaces. Something interesting is that there are not symmetric tensor functors to the categories that we know that were our examples in characteristic 0, basically, vec and super vec. And this is a cute fact. If you are, for example, in characteristic here, P is 5, when you do the square of the L3, you get L1 and L3, this sum. When you look at the dimension, if there is a notion of dimension, the dimension is multiplicative and additive, and the unit has dimension 1, you get the golden radio. And a symmetric tensor functor needs to send objects of certain dimension to the same dimension, and here the dimensions are the dimensions of vector spaces, so they are natural numbers. So we see that here we have some nice exotic behavior. So what all this thing about verb P, right? Why are we so excited? Let's remember here a little bit. I will give you, I mean, I wrote it recall, but it's a new version of the linear theorem. It's the same theorem, but it has a new way to say it. Again, remember that we care about this moderate, maybe let me change the color, moderate growth, symmetric tensor categories. And I told you in characteristic 0, for symmetric tensor categories of moderate growth, the linear told us everything that we needed to know. He told us that needed to be rep G for G and affine group scheme. Other way to say that is this one, more in terms of symmetric tensor functors, because we were talking about symmetric tensor functors. I told you one way to understand the categories is through the functors that we care. Okay, so a way to translate the linear theorem is that instead of telling you directly the group, it's telling the story about in a way at looking at the tensor functors. So if you have a symmetric tensor category of moderate growth in characteristic 0, there's always one of these symmetric tensor functors to super vec. So super vec is kind of a very important object, kind of universal object in this symmetric world, moderate growth in characteristic 0. And maybe I wanted to mention here that the other version I was telling of the theorem is kind of a reconstruction theorem. So the idea is that you can prove first these kind of theorems, that you have the symmetric tensor functor, and now using this functor, you can go back and construct your group and express your category C as representation of some object that you understand better. Like, for example, in this case, yeah, the affine scheme. But how we do that, looking at some nice, yeah, it's called Tannakian reconstruction, and it's related to the natural transformations of this functor. But there is a way to do it. I wanted to mention because it's an important perspective that people studying this field has. And there was a very beautiful theorem by Victor Ostrich that kind of opened the game to look at characteristic P again. It's where these Verlinde categories appear. And what he proved was a kind of a generalization of the Ligne's theorem in characteristic P, but in the fusion word. The fusion word was the square that I wrote you as a, oh, let's look at this cute example. Fusion, remember, is semi-simple with only finitely many simples. So now if I'm, okay, maybe let me add one word that I forgot, and it's very important. If I'm looking at symmetric tensor or symmetric fusion categories, here I need to add the word symmetric, that's what it's missing. And I'm in characteristic P now. I'm not asking moderate growth anymore because here I have finite, so I'm even more moderate, basically. But now I'm in characteristic P. Victor proved a similar result to the linear, but now the universal object, instead of being super big as before, now are these exotic Verlinde categories. So, of course, we always want to know, can we do better? Can we remove fusion and go to moderate growth? And the answer is yes. Sometimes people can do better. Columbier, Tinkoff, and Ostrich have been doing amazing work on this topic, on these symmetric tensor categories. And they studied the case of semi-simple. So we have here semi-simple symmetric categories of moderate growth. So more similar to the linear, but with symmetric here, and in characteristic P. And they can prove that there is always one of these symmetric tensor functors into Verlinde. This was conjectured by Ostrich in his original work, but took like 10 years to get this result. And there was a lot of technology that needed to be proved. And there is a follow-up version of this, but I will not talk about that. It's about some Frobenius functors and some other characterization of things that when this functor exists, another characterization. Question, is moderate growth really needed here? We don't know. This is an open question. So this is open. I mean, this green probably is not showing very well, but it's an open question. But what about this hypothesis here, this semi-simple hypothesis? We really need it. In positive characteristic, we really need it. And this is also really fun about this topic, or I think in math in general, how these kind of questions lead to a totally new field of study, right? Or maybe subfield of study. But in Venkatesh was studying in characteristics 2 some examples of non-semi-simple things, and he was able to cook up some nice Hoff algebra, which is a counterexample to this. And then Benson, Ettinghoff, and Ostrich were studying this in more general for any characteristic, and what they were able to come up is with families of symmetric tensor categories that you see they will embed. This is the one that we were talking, the semi-simple, but now for each power of P, you have a new one, and all these are non-semi-simples. And they don't satisfy this. And then you can create using that, the union of that, this ver P infinity. And there is a conjecture by Benson, Ettinghoff, and Ostrich that if you have a symmetric tensor category of moderate growth, now we remove semi-simple, and you're in characteristic P, then there should admit a tensor functor, but now the output, instead of being a spec or ver P as before, are these infinite, like ver P infinite. And here the word unique is there, and maybe it's for a question why I add the word unique there. Actually, the word unique was also up to some isomorphism in all the other theorems. I just didn't include it because I wanted to focus on that point, but at this point, I wanted to mention also that uniqueness. So maybe let me try to go to the point of the results with Ivan and Guillermo, that it's about Lie algebras in symmetric tensor categories. There are a couple of motivations. I'm giving you here one motivation. So if you have Lie algebras in superbag, for example, these Lie algebras in superbag correspond exactly to super Lie algebras. Sorry, I forgot the word Lie. Super Lie algebras in vector spaces. So honest Lie super algebras. And that's interesting because sometimes questions that are hard to answer in one word are easier to answer in the other. So we kind of wanted to understand this game in a more general setting instead of superbag specifically. What about other settings, other symmetric tensor categories? So what would be a Lie algebra in a symmetric tensor category? Here I'm telling you very quickly this definition, but it's a very subtle definition and has a lot of things, but the idea is here. So what would be a Lie algebra in a symmetric tensor category? It will be to start an object in the category, and I want to have my bracket in the category, which will be anti-symmetric, like the bracket that I wrote before, but now I'm writing it in this way as a map in my category. I want to satisfy some version of Jacobian. I'm not writing it here, but there are some things that you need to be delicate about, and specifically there are some extra conditions to make this definition precise. But the idea is that it's more or less similar to what we have in the usual word, but now in the category C. All these maps and all these conditions need to happen in your category C. Why we care about Lie algebras? Because I already told you in the first part of the talk that if I have a Lie algebra, the modules give rise to a symmetric tensor category. So now, if I have like a more exotic symmetric tensor category, I can define modules in the same way. An object in G that has some nice action, in C that has some nice action of G on it that satisfies some compatibility, but I can look at the modules, and now I can look at the collection of modules in C, and that will give me a symmetric tensor category again, and actually this will have a functor to my category, my original category C, and that will give us information. So how we construct these Lie algebras, in particular in VERP. For this, I told you a definition of VERP that was a semi-simplification of the representation of the cyclic group of order P. But actually now if we switch a little bit and we look at another description of VERP, it will be more easy to describe Lie algebras. So VERP can be also defined as the semi-simplification of the representations of these. So here I have polynomials on T, but I will kill the power P of T. And so what is important here? What will be a Lie algebra here? It will be an honest Lie algebra in vector spaces and some derivation that when you do order P, it gives you 0 coming from this relation. So why this was very interesting? Because using our semi-simplification, this is our semi-simplification functor, Cannon, what he was able to do was able to find Lie algebras in VERP. He did it in very specific examples using the semi-simplification factor, and that was nice because he recovered exceptional Lie superalgebras using this idea that supervec is inside VERP. So for Lie superalgebras, there are some exceptional cases, and people wanted to understand why they existed, and one way to understand it is like that. Looking at VERP contains supervec, and semi-simplifying regular Lie algebras, you can get this. And what if you start with something that maybe it's not a Lie algebra? Can we anyway cook up some Lie algebras? The answer is in some cases, yes. El Duque and a lot of collaborators, different collaborators in different papers, he was working on that. He has different works on that. With Ettinghoff and Cannon, they talk about Jordan algebras in characteristic 5, and also with Daza Garcia and Sayin, and with Cunha, they work and study composition superalgebras to get new Lie algebras. Let me tell you our perspective with Guillermo and Ivan in the last minutes. So there is a very important class of Lie algebras, usual Lie algebras. What is the input? It's some kind of Cartan matrix. And what is the output? It's some set-graded Lie algebra that satisfies some nice things. Why? What? A triangular decomposition. This part is in degree 0 and it's abelian and has some specific basis that I call HI. And this one will be generated in degree 1 by some EIs and this one by some FIs in degree -1. The brackets are given by this matrix. So HI and EIs are just a multiple of the EI given by the corresponding entry of the matrix. When you have an F, now you add a minus, and EI and FI will live in degree 0, and it will be HI or 0, depending if the label is the same. This is not super important now, but if you have something that satisfies the three things, it will have a projection to the one that was defined by Kaka and Moody independently. Some nice things about this. These mimic Lie algebras of matrices. They can be extended on the super cases if you work well the parity of the generators, the generators of the different pieces. And in characteristic 0, every semisimple Lie algebra can be given or is one of these. Contragredient Lie algebras are related to this, but they are related to having some root system. I know that I'm running out of time, so I will kind of go a little bit faster. And the idea is that it's really nice that you will decompose your Lie algebra in some, again, triangular decomposition as usually. You have that your EIs that come from the alpha i's, where I have only one in the component I. This EI will live in this component, the FI will live in this component, and then the HI will live in 0 component. But now if I take something in another component, there is always some automorphism that takes this one to one of these ones, and that's the Weil group. So what it's important to keep in mind is that there is a rich structure, and one very important thing to keep in mind is that this one is always one of the derivations that we wanted of order P. So what we prove with Ivan and Guillermo, and this is part of the work in the Órbita journal, is that if you start with a classical CAC-Moody or contragredient algebra, and you took this distinguished derivation for some I that the Cartan matrix doesn't have 0 in that point in the diagonal, then you can semi-simplify, and you have a nice new root system that it's not classical, but it's coming from some parabolic construction. And we can describe well this, and we have a nice, okay, maybe this I will not say because this is more technical and I'm running out of time. I wanted to emphasize that. But what it's important is that we can recover the abelian part. But if you see here, there is a change. It's not just the semi-simplification. We added this that we call the ghost, that it's coming, in the case of Verlinde, from L3, and that it's giving us a copy of SL2 there. So basically, if you are in VerP, you can get new Lie algebras by semi-simplifying contragredient Lie algebras using this nice derivation. We use this specific example. And then we wanted to know if there are more algebras. And what we were able to give you is a recipe. If you have a Lie algebra in C and you have some action, so you have a module, but also some way in which the module and the dual of the module behave, this map need to be of X modules, then you can cook up a set-graded Lie algebra in your symmetric tensor category that behaves nice. In degree 1 is the module. In degree -1 is the dual of the module. In degree 0, our torus is the original Lie algebra. And we have a nice description in terms of some semi-direct product and the quotient of how the interaction of the things is. And this is the maximal set-graded quotient with these properties. Maybe I will stop here. Thank you.
Thank you, Julia, for this very nice talk. So maybe now I open for questions from the audience. Well, I have a naive question. So you at some points in your presentation, you left out the characteristic 2 case, but then later on you mentioned some interesting examples in characteristic 2. So can you say something what goes different and what are the subtleties in characteristic 2?
You need to be more careful on how you define the things, but you can define it. It's just that some things will not make sense for the anti-symmetry or things if I write it in the same way, because I'm basically saying that everything will be abelian as I wrote it, because I had -1 and 1. So you need to touch it a little bit, but you can still define things, yes. And it's very interesting, usually, characteristic 2. For the Verlinde categories, is a little, weird, but the most exotic examples appear in Ver 5 or up. But for example, this one that I was saying, that you look at Ver P square and all that. So you have Ver 2, but then you have Ver 4, and Ver 4 is super interesting. It's small, and it's a nice toy example to try to really get your hands dirty and understand this non-semi-simple thing. So I think characteristic 2 is perfectly fine. It's just that sometimes you need to be more careful when defining because of the minus and the anti-symmetry and these kind of things.
Okay, thank you. So let me see if there are any more questions from the audience.
Can I ask a question?
Sure, please go ahead.
Thanks. Yeah, I was wondering about those higher Verlinde categories that you mentioned, Ver P squared, Ver P cubed, and so on. Are they still related to modular representations? So Ver P is the semi-simplification of representations of the cyclic group,
yes,
right, in characteristic P. But what about the others? Where can you say anything about where they're coming from?
It's a little bit technical. I mean, I maybe can say something. I mean, yeah, they were, so they are abelian. So these categories are some, yeah, I like abelian envelopes of some quotient of some categories of tilting modules. It's more coming from that side, if I had to say. Maybe there is another description in the way that you are saying, but so these Verlinde categories can also be thought from the category of tilting modules of SL2K. And when, or this work of Benson, this is work of Benson, Ettinghoff and Ostrich, not mine, the higher. But my recollection is that they were trying to understand some quotients of these tilting modules that were not in principle abelian when they were taking, and then they took the abelian envelope of these kind of things to get the VerPN.
Okay.
I don't know if that's helpful. I don't remember if there is a
Mhm.
connection, but maybe since you asked this, actually, Colombier, Ettinghoff and Ostrich proved really nice things about modular representations using this. That's one of the motivation, that some problems are very hard in some setting, but when you go to this other setting, maybe you get answers. So it's useful for that, but I think it was the regular Verlinde. I should double check.
Okay.
Yes.
Okay, thanks. Thank you.
No worries. Thank you for the question, Marcelo.
Are there any more questions? Well, if not, then let's thank Julia again
There
for
is
this
one
talk.
in the chat.
Thank you, Julia.
There's a question in the chat.
Yes.
Oh, I'm sorry. I'm sorry.
I didn't see it, sorry.
I have what can we say about non-semisimple category C if we already know its semisimplification?
A lot of the properties, no, okay, let me see if we already know is this a semi-simplification. I'm not sure if I understand the question. Let me see if I understand. So you want to start with a non-semi-simple and take the semi-simplification and be able to say something about the semi-simplification, about the result, Alfonso? Or about the original? Maybe, I mean, about the original.
About the original.
Yeah, one question is how much you can reconstruct, I would say, but I think that's a hard question. What it's true is that a lot of the properties are preserved. So if you understand for some reason better the semi-simplification and it has some nice property, potentially the original category also, you could try to check if the original category has that property, like, because it's well behaved, the semi-simplification, and you have this nice functor that, yeah, it doesn't satisfy all what you want, but at least part of what you want. But I think it's an interesting question, but I think it's maybe hard. Because as you saw, for example, Verlinde is the semi-simplification of many different things. So you could have many original categories that give you the same. So I don't know if it's that easy to, or what kind of things you can recover. But I think it's a great question to see if there are some set of things that you could recover. And maybe let me say one more thing about this higher Verlinde that Marcelo asked. There is a conjecture about how the cohomology looks. We know that it's finite generated always, the cohomology, which is an open question in general for finite tensor categories. It's a conjecture that it's true. For this one, it was proved by Benson, Ettinghoff, and Ostrich that, or by Benson and Ettinghoff, that it's finite generated, but there is only a conjecture on how it really looks. So there is a lot of interesting work that people could do in this. And the other thing that I didn't say, and I will say it now, it's that all these symmetric, like Lie algebras, are also important to get group schemes in Verlinde categories. Venkatesh has a classification, so they are one of the ingredients. That's why we also care about it, but I didn't have time, so yeah.
Okay, so let me see if there are any more questions. I don't see anything in the chat, so last chance if someone wants to ask Julia. Well, if not, then Julia, thank you so much for your talk, and thank everyone for coming. Our next webinar is going to be announced soon. It's pre-scheduled to take place in 29th of October. So I see you all there.
Thank you again for the invitation. It's a pleasure to be here. Thank you.
Thanks.
Recording stopped.
Thanks a lot.
Okay, bye-bye, everyone.